Good morning, everyone. Thank you for joining our webinar this morning, the PCM Masterclass. Since seems like everyone has joined, we will begin at this point. A few housekeeping comments before. All participants were muted upon entering. If you have any questions at any time, you can simply click the question and answer button at the bottom of your screen and send it our way. We will hold all the questions, though, at least till the end of each section or the end of the webinar to try to fill as many as possible. If you do have any other questions or suggestions for any future webinar topics or anything about our company or organization, please include those in the question and answer window as well. So welcome to today's masterclass, using phase-changing materials to improve thermal packaging. First off, I would like to go over our presenters. Thank you for their time to do this today. We have Rich Fermato, who will be starting today. He's the Director of New Technology for the Kabu Group. After Rich presents, we'll have Iftikhar Ahmed, the Director of Thermal Engineering. We also have Don Mance with us today, a Business Development and Sales Manager, and then myself, David Hahn, I'm Product Manager here at the Kabu Group. So without any further delay, I'll turn everything over to Rich, and he can start going over the overview that he has today of phase-changing materials.
Hi, everybody. This is Rich Fermato, Director of New Technology at Microtech Labs, Kabu Group. Happy to be here. I'll be going over the overview of phase-change materials. So PCMs are materials that can absorb, store, and release thermal energy. They release large amounts of energy upon freezing, which is typically termed the latent heat of crystallization, or delta HC. And they also absorb large amounts of energy upon melting, which is the latent heat of fusion, or delta HF. On the chart on the left, basically, we're showing PCM or a material exhibiting sensible heat, and on the right, we're showing a PCM material exhibiting sensible heat and latent heat, which is the flat line at a constant temperature. In this case, with added heat, it's the melt point. I wanted to say for this presentation, we're going to assume PCMs that phase from solid to liquid. Other transitions such as liquid to gas, solid to gas, solid to solid aren't considered. And the term latent heat is sometimes interchanged with the term enthalpy. And the enthalpy, however, is defined as internal energy plus PV work term. And in this case, that's 0. So the enthalpy and the latent heat in normal cases is the same. So PCMs, as I said, they allow thermal energy to be stored and used at a later point in time or transferred to a different location to be used in some other process. The latent heat is a large amount of energy. If it's applied correctly, you can enable long durations at the phase change temperature. And this normally takes place at a quote-unquote constant temperature, which is referred to as the melt point, or the crystallization point if you're cooling. And this typically occurs in either a constant temperature or within a narrow temperature range. It is important to note that in real applications, the melt temperature is usually not the same as the crystallization temperature, and the difference is typically termed supercooling. Thermodynamically, the melt point and the freeze point will be the same in the ideal non-obtainable case of a perfect crystal of material that's heated or cooled infinitely slowly. So the heating and cooling rate do affect the actual value of the melt and freeze point. The faster the heating and cooling rate, the larger the difference between the melt point and the crystallization point. There are basically two types of heat energy storage, sensible heat and latent heat. Sensible heat is the energy needed to change the temperature of material without phase change. It's numerically indicated by specific heat capacity, C sub P, which is the ratio of energy per mass to temperature change. The latent heat, on the other hand, is the energy required to change phase of a material from solid to liquid, liquid to gas, or vice versa. Water is typically considered the ultimate PCM. It's very common, it's readily available, low cost. The change takes place at the melt point and the crystallization point that is 0 degrees C from solid to liquid. Water has a relatively high latent heat, which is 334 kilojoules per kilogram. It has a unusually high specific heat capacity, especially in the liquid phase, which is about 4.2 kilojoules per kilogram degree C, and it's used extensively in refrigerated shipments. So as I mentioned, for water, the melt point and the crystallization point are very close to each other, as is the heat of fusion and the heat of crystallization. In the majority of cases, this is for normal materials, this is not true. Water has a specific heat that is about twice as much as the liquid phase compared to the solid phase, which is ice. So the advantage of water's high specific heat has been used in thermal packaging applications, and prior to mainstream use of PCMs, thermal systems had to be designed with water-based gels and bricks in contact with the product.
Rich, let me interrupt you real quick 1 second. Your microphone seems to be crackling a little bit. Try to alleviate that concern.
Okay, I'll do it now.
Okay.
Okay, I'm back. How is that?
That sounds much better. Thank you, Rich.
Sorry about that.
No problem at all.
Here we have the phase change diagram of water from ice to vapor. As you'll note, the solid phase is shown on the far left. As we proceed through phase change from solid to liquid, that flat line is the latent heat. As we proceed up the curve from liquid to vapor, that is the slope of that line and represents the specific heat in the water phase. And then the large line where it's shown liquid to vapor, that is indicative of the heat of vaporization. And then, of course, the vapor phase specific heat is indicated by the line on the far right. So again, it's important to note that each phase has a different specific heat, and it also should be noted that frozen water, which is ice, has a density that's lower than liquid water, which is why ice cubes float in water. And this is uncommon. Most materials, including the organic PCMs that we will be discussing here, do not exhibit this characteristic. So there are several classes of PCMs that can be used with thermal packaging. First, it's important to note that the most common ambient environmental conditions for thermal packaging are typically between less than 0 C to 32 C. That is the ambient temperature to which the packaging is exposed. And in the thermal packaging industry, there's typically several profiles, temperature ranges that are considered. There's frozen, which is less than 0. There's refrigerated, which is 2 to 8. And there's controlled room temperature, or CRT, which is 15 to 25 C. And based on those temperature ranges, there are some organic PCMs and some inorganic PCMs that fit into those temperature ranges. The organics are characterized by paraffins, fatty acids, esters, including fatty acid methyl esters, and alcohols. And the inorganic PCMs are typified by salt hydrates and saltwater solutions. So it should be noted here again that the PCM classes used for thermal packaging is significantly reduced based on the product temperatures. Some PCM manufacturers use combinations of these to make products that meet specific requirements. Also, within a given class of materials, blending is commonly used to target a desired or specific phase change temperature. For example, you can make a 3C PCM with a mixture of C14 tetradecane with C16 and hexadecane. Purity is also another important consideration. Both the latent heat and the sharpness of the phase change temperature can be significantly improved with the use of high purity materials. So selection of PCM class is obviously something that's important, and there's a number of different characteristics that should be considered. Obviously, the Phase change temperature is very important. Ideally, you'd like to have a sharp melt and freeze point. High latent heat is obviously important. The higher the latent heat, the less material you need for a given application. PCM should be commercially available at low cost. They should have good thermal cycling stability, so that means limited supercooling and hysteresis. They shouldn't react with the packaging and or the adjacent materials that they're up against. They should be non-toxic and non-carcinogenic. They should be ideally sustainable, so compostable or recyclable. They should be low or non-flammable, so that implies a high flash point or a low vapor pressure. Also non-corrosive and low volumetric expansion and contraction upon freeze thaw is something that's desired. So no class of PCM meets all of these characteristics, but this listing can be used to down select the optimal PCM for an application. It is also important to note that the volume change depends significantly on the type of phase change. For example, ice to water volume change is much lower than water to vapor volume change. And the difficulty in handling the large change in volume, such as water to water vapor, has resulted in the industry being dominated by the use of ice to water phase change. Here, we put together a table that shows basically the types of phase change materials for thermal packaging and the pros and cons of each. I'm not going to go through the entire table, but I will say that in general, all of these materials as liquids are considered difficult to package without leaking. Hydrated salts and saltwater solutions are, in my experience, very difficult to package without leakage. Also, alkanes are actually biodegradable, which is something that not many people are aware of. They can also be oleo-sourced, and they can be, if they're made shape stable, alkanes specifically, then they can avoid the liquid aspiration hazard in their liquid state. And for the fatty acid methyl esters, it should be noted too that some non-methyl ester PCMs do not react with polystyrene. So there are esters that are compatible with EPS. Alkanes and methyl esters, from my experience, dominate the packaging landscape, but suppliers have also developed fatty alcohol and fatty acid-based solutions. To date, from what I've seen, salt hydrates have not really gained mainstream use in thermal packaging due to their poor cycling stability. Basically, their composition changes with cycling, and their difficulty in manufacturing. Salt water solutions, for example, sodium chloride and water, eutectics, are widely used for frozen applications, such as I mentioned, the eutectic of salt water, and salt water solution has a phase change temperature of -21 degrees Celsius. So for PCMs in general, they have significant thermal energy benefits, as I discussed previously, and the materials in the cases that we're looking at typically cycle between solid and liquid. So for the majority of applications, PCMs will need to be contained because when they reach their liquid state, that containment is necessary. And there are various containment methods available, but the primary methods, if you want to look at kind of the top line, would be macro encapsulation versus micro encapsulation. And there are other available containment methods, but again, for the sake of time, we're just going to discuss the macro and the micro encapsulation in this presentation. Here we show some of the typical macro encapsulation that's used in the industry. For example, on the upper left, liquid in a flexible pouch. On the upper right, gel in a flexible pouch. On the lower left, liquid in a rigid polyethylene bottle. And on the lower right, liquid in a foam brick. So these are kind of the typical formats that you will find for microencapsulation. To combat liquid leaks, organic PCMs in flexible pouches typically they actually use a fail-safe, which is typically termed double bagging. So they actually bag the packaged liquid in the flexible pouch. They'll actually put another bag over that to avoid the possible contamination in the liquid state. The use of rigid bottles, as shown, is an excellent solution to combat this, but there are form factor, basically size limitations because it's a molded product. It requires new tooling for each size. And as we'll discuss in upcoming slides, Microtech has developed some AdaptTech rigid PCM panels, which is basically a microencapsulated PCM polymer composite, as well as shape-stable gels, which we call Shift, and they can be formulated with any organic PCM. So the pros of macro encapsulation, obviously it has a container around the PCM in its liquid state. It's relatively low cost. Typical, like I said in the previous slide, consists of a flexible polymeric blown film or a rigid high-density polyethylene blow-molded container. Obviously, if it's a liquid phase, it utilizes 100% of the latent heat. These can be made quickly and cost-effectively on standard packaging equipment, and by that I'm talking about the flexible polymeric film type containers. Rigid molded containers create a durable, reusable product, and some novel advancements, such as a shape-stable or gelled PCM, when combined with flexible film packaging, allows reuse with lower costs and a wider form factor than the rigid blow-molded containers. Standard packaging equipment that's referenced here includes machinery such as sachet, vertical and horizontal, form, fill, and seal, and inline thermoformers. Here we touch on microencapsulation, and basically what this slide shows is at the top center of the PCM in its solid state. As the temperature rises, the PCM melts and creates a cooling effect. When the PCM then is fully melted in its liquid state, it is encapsulated within its shell. As the temperature falls, it solidifies, energy is released back into the environment, creating a warming effect. So this is basically the standard phase change as shown in a microencapsulated PCM. For reference, the particle size we're typically talking about is 15 to 25 microns. The polymer shell typically comprises 10 to 15% by weight of the package, with the PCM comprising the remainder. And it's important also to note that spherical microencapsulated PCMs are typically what's made, and this is a benefit because it's the most efficient packaging shape. And the pros of microencapsulation, it's a microscopic container around the PCM core. It prevents leakage, degradation, and contamination. You can use it over and over again. In our product, it's available in wet cake, which is 70% by weight solids in water, and also in dry powder, which is greater than 97% by weight solids. And it can be incorporated into a variety of materials for multiple applications. So we specialize in the development and commercial production of microencapsulated PCMs over a range of phase change temperatures. These are incorporated in materials such as foam, like mattresses, pillows, helmets, electronics, such as thermal interface materials, packaging and external cases, buildings materials, such as paint, concrete, and drywall, and also textiles, so activewear, apparel, and linens. The use of microencapsulated PCM in thermal packaging has been somewhat limited due to higher cost and limited number of suppliers, but Microtech has developed a new technology to address this, the AdaptTech rigid panels, which, as I mentioned previously, is a microencapsulated PCM polymer composite, and this is now being made on a commercial scale. That's basically the conclusion of my section. I don't know if we want to go with some questions now or if we want to continue on. I'll let Dave make that decision.
At this point, Rich, we'll just keep moving forward. So thank you very much for the overview of phase change materials as well as uses of them and applications of them in a micro and macro encapsulated way. We will move on now to the director of our thermal engineering, Iftikhar Ahmed, for the applications of PCM and the use of them in thermal modeling.
Good morning, everyone. This is Iftikhar Ahmed. Thank you, Rich, for a very comprehensive presentation on PCMs. In my section, I'm going to talk about the use of PCMs in temperature-controlled packaging, and also how to use thermal modeling tools for design optimization and PCM selection in packaging applications. So the objective of temperature-controlled packaging is to keep product temperatures. These are temperature-sensitive products, mostly pharmaceuticals, vaccines, etc. So to keep the product temperature stable for a specific shipping lane and a specific duration. The design approach is to isolate the product from the external conditions or the ambient conditions using phase change materials. And these phase change materials, by absorbing or losing heat to the external environment, will provide a stable temperature for the product. In front of you, there are two different examples of how PCMs would work in a packaging system. You have the product in the center, and it is usually surrounded by phase change materials. So on the left side, if we are shipping against a hot ambient environment, we are using water gels. Water is the most common phase change material which is used. So the water gels are frozen at -20. They are surrounding the product, and the heat from the external environment is absorbed by this frozen material until its temperature reaches the phase temperature of water, which is 0°C. At that point, the water will start changing phase, and that will maintain temperatures inside the product case. On the opposite side, if you are shipping against a cold ambient environment, where the temperatures are below the phase change temperature of water, that is below 0, then the PCMs that are being used are refrigerated, which is at 5°C, and then they will start losing heat from the PCM to the external environment until they reach the phase temperature of water, which is 0°C, and then it will start freezing, thereby maintaining the temperatures inside the product case. There are many different ways for placement of PCMs inside a packaging system. And what I'm showing you are three very common ways of doing it. There can be multiple configurations and combinations of different refrigerants. So these are one of the more basic ones. The most simplest one would be a two-sided pack-out, where you have refrigerants which are placed on just the top and bottom of the product. This type of approach would be used when you have a product case where the height of the product is much less than the length and the width, so thereby minimizing the surface area from where heat can come in. Now, the objective of trying to keep the PCMs to a minimum quantity is obviously to reduce the shipment, the weight of the shipment or the container. That obviously contributes to its cost. However, at the same time, it's a kind of a trade-off between making sure that the product is properly protected as opposed to saving on the weight of the container. So a two-sided approach would be usually for a shorter duration, about 24 to 36 hours. Anything more than that will not be possible with this configuration. You can go to the second approach, would be a four-sided refrigerant, where you have refrigerants placed on four sides of the product, where the two sides are exposed. However, again, those surfaces should be relatively smaller compared to the larger surfaces where the PCMs are placed. Again, this type of configuration would be for a medium duration shipment between 48 to 72 hours. And finally, the most complete product protection would be a six-sided refrigerant approach, where PCMs are placed on all six sides of the product, covering it completely. So surface coverage is very important. especially if you are looking at shipments for long durations between 70 to 120 hours. I'd like to add here one more thing is that these configurations can change depending on what insulation material you use. So what you're seeing in front of you are the examples of using an EPS container. However, if you increase the R value of the container or the insulation value, then these configurations can be changed. For example, if I increase the insulation of the container from EPS to a VIP, then I may be able to use a two-sided approach for a longer duration. So what are the factors that you have to look at for selecting the right PCM for your application, for your packaging system? The main factor would be to look at the product temperatures that need to be maintained inside a particular shipping system. There are three main categories in the pharmaceutical packaging business. The refrigerated temperatures, which are the most common, between 2 degrees centigrade and 8 degrees centigrade. Then there is the CRT, which is controlled room temperature between 15 degrees centigrade and 25 degrees centigrade. And then finally, the frozen, which is below 0 degrees centigrade. So in terms of PCM selection, you have to select the PCM for any of these three applications depending on the temperature range. So a PCM to maintain refrigerated should have a phase temperature which is within that range of the product temperatures. Another factor to consider would be how this shipment is going to be made through the year. Is it a universal shipment, which basically means that you want to use the same kind of configuration, whether it is summer or winter, year-round, without changing any of the configuration or the conditioning requirements? Or is it going to be a seasonal solution, which basically means that you have a particular configuration of PCMs in the summer and then another one for the winter? There are obvious issues using a seasonal approach because you will have to then decide during the year when to switch the design for a winter configuration from a summer configuration. Typically, if you are using a seasonal approach, water-based solutions are adequate. They do have their risks, but if you want a fail-safe solution where you don't have to worry about changing in weather conditions, then using PCMs and a universal solution is the most optimum way to go. Now, the use of PCMs has become much more common over the last 15, 20 years. And previously, I think Rich mentioned in the section that people had been using water more frequently. However, water has its own limitations. One of the big limitations of seasonal solutions. So with PCMs now, it's possible to use universal solutions, which are not dependent on the season of the year. Also, CRT solutions are also possible using PCMs. So control room temperature solutions, it is very difficult to use water to maintain temperatures between 15 to 25 C, especially if you are shipping under cold conditions. So in those situations, a PCM which has a temperature range within that 15 to 25 C is much more stable and can provide that kind of protection. Another area where more successful solutions are available now using PCMs is for frozen shipments. Previously, when you talked about frozen, you either used a eutectic salt brick, which phases around -20, -21 C, or a dry ice, which is -79 C. However, there are now specific products which have different temperature requirements below zero. Like, let's say you have a product which needs to be shipped between -20 and -40, then you cannot use dry ice there. So in those situations, we have engineered PCMs which have specific phase temperatures in those ranges that can be used. Another important factor in using and selecting PCMs is the useful life of a PCM. There is a trend now and an imperative in the industry, in the packaging industry, to move towards sustainable packaging, including the use of reusable systems rather than single-use systems. So when you're using a reusable system, you want to make sure that the PCM that you're using can perform multiple times during reuse consistently. So the thermal cycling data becomes very important. that you get the same consistent thermal properties like phase temperature, latent heat, and density performance the same time every time the PCM is reused. Environmental considerations are also important. You want to make sure that the PCMs have, in terms of their toxicity, reactivity to other components in the packaging system, sustainability, and recyclability. So those are all the factors, and some of the PCMs that Rich talked about in his section, the organic PCMs meet a lot of those requirements compared to some other kind of PCMs. Another factor is preconditioning requirements. So PCMs would have to be conditioned. There are different ways of conditioning them at different temperatures depending on their phase properties. So those would have to be looked at also in terms of what conditioning equipment is available. Usually commercial freezers and refrigerators are available to people who are doing these kind of shipments. Freezers operate between -20 and -18 C. Refrigerators operate around 5 C. So if you have PCMs which can be conditioned at those temperatures, that is the most optimal because that doesn't require any special equipment or special conditioning. Sometimes you have to use warm-up or bench times where you condition a PCM at a certain temperature, and then you have to put it at room temperature before it reaches a certain temperature at which it can be packed out. Cost of PCMs is another factor to be considered. Cost of some PCMs will be higher than others, and especially if there are blends of PCMs because they require more engineering and development. So those will have to be considered as well. This graph actually is there to show you the effect of the use of different PCMs and how they impact the temperature stability and duration of a particular packaging system. So the graphs are basically the phase change graphs of different types of PCMs. You have water, PCM4, eutectic salt, and PCM18. They're all subjected to an ambient condition of 40 C. And you can see that the orange curve represents water, which phases 0 C. The latent heat and the density and the volume of the PCM used, in this case 56 ounces, determines the duration at which it will maintain their phase temperature. As you go to a PCM4, you see that the latent heat is much less, so it will not maintain the same duration. When we look at a eutectic salt, which phases at -20, even though it has a significantly higher latent heat and density, it still does not provide us with the same amount of duration. And the reason is another factor that contributes to the how long it takes for it to phase is the delta T, or exposure to the external temperatures. So in this case, the delta T between the eutectic salt and the ambient is about 60 C compared to water, which is about 40 C. One of the important tools that we can use in selecting PCMs and doing design optimization of packaging systems is thermal modeling. Thermal modeling is essentially modeling tools, simulation tools, which use math models to analyze and solve for thermal physics in a particular configuration. And the approach of thermal modeling essentially is that you start out with a particular design configuration. In this case, on the left, you see it's a pack out which consists of a EPS container. There are 2 water gels in there. There is a corrugate buffer, a sleeve, and there is a single product vial, which is a vial carton. And the objective would be to look at this configuration, run a thermal simulation, and get a comprehensive temperature results on it to understand whether this particular option is going to work successfully for the required conditions. However, if you do not have these kind of tools, then basically you are left to do trial and error in a thermal test chamber, which can take weeks to months. The approach for thermal modeling is basically you take the particular configuration you're interested in, you develop a 3-dimensional geometry from it, and that 3-dimensional geometry is then used to create a discrete math model, or what we call a finite element model, in which individual components like the gels, the vial carton, the insulation container are all meshed using discrete elements. In the same process, you define the thermal properties, the physical and thermal properties like density, latent heat, and phase temperature of the different components. And then you define the boundary conditions, the initial temperature, the conditioning temperatures of the various components, the external ambient profiles, and then you run the solution. The solution basically consists of temperatures versus time. So it's a transient thermal analysis, and that gives you a comprehensive thermal map of your system. So some of the results that you get from thermal modeling is, on the left, you can see a complete 3D temperature map on the entire system, where it is the insulated container, the gel, and the vial. You can also drill down into more detail on the product, which is really what we are interested in, what would be the product temperatures and the thermal response of the product for the duration of the shipment. And then you can actually probe at different locations on your product and get the temperatures versus time plots. Another aspect of thermal modeling is that you can obtain results on your PCM as well. So this is a gel phase quality plot. Phase quality basically indicates the solid or liquid state of the PCM. So in this case, these are the two water gels that are being used, and they start out frozen. So the 0 on the legend indicates that the gels are solid at minus 10 degrees centigrade. And as it absorbs heat from the external environment, it will start phasing. And it will go from 0 to 1, 1 being the fully liquid state. Another interesting thing to note about this plot is that as the phase change begins and the gels absorb heat, they start phasing right at the corners, because those are the areas which absorb the most amount of heat and they have the most exposed surface area. And the central part of the gel is the one which will phase the last. The results obtained from thermal simulation can be very accurate, within 85 to 90% of your test data. So they are very useful in optimizing your design and saving you a lot of time, which otherwise would be spent in doing a lot of trial and error exercises. It will give you a complete three-dimensional map. Here's an example where you can see the simulation results, which are the blue curve on the plot, and compared to the thermocouple data, the actual test data for the same product, which is subjected to an ambient profile. The green curves represent the chamber ambient temperatures. What I'll do now is I will show you some case studies where the use of PCM provides the benefit of having much more optimized design, and sometimes getting a successful design where no solution existed before. So in this case study, we have a insulated container which consists of products surrounded by water gels at 5C conditioning. The design was originally made for a ISTA 70 winter profile for 48 hours, so it would successfully work for that winter profile. The amount of gels being used is about 21.7 pounds. However, once you have a qualified shipper to a particular standard profile, like a ISTA profile, it is possible that your shipping lane might change, and you may actually obtain real shipping lane data, and you would want to know what will happen to your shipper in those kind of new conditions. So in this situation, thermal modeling is very useful, because if you already have data, you can use that to develop a accurate thermal model, and then you can input different shipping lane data to see the thermal response. So in this case, we inputted the new extreme winter ambient profile, and when we saw that this would not work, actually the design would fail at 26 hours where the temperatures would go below 2. In the next slide, I'll show you the results. So this is the original design, which was qualified to the ISTA 70 winter profile, a 48-hour profile. It's basically the cyclical profile using 24-hour cycles. And you can see the temperatures are within the 2 to 8 requirement of refrigerated product. Now, as soon as we apply the new winter profile, where you have a significant soak at minus 15 degrees centigrade right in the middle of the shipping lane, we see that we're using the 5C water gels. you will see the temperatures of the product go below 2C around 26 hours. So this is not really a good design for the new profile. So for what would be the solution? So the solution would be that we use the same container. We don't want to change the container, but we switch from the water gels to a PCM which phases at 4 degrees C. So this PCM4 will be used instead of the water gels. And then another thing we notice is that as soon as you use the PCMs, you are able to actually reduce the mass of the PCMs. Sorry, there's a mistake there. It's a total of 6 rather than 8. So you reduce the original 21.7 pounds of water to 17 pounds of PCM. And the reason essentially is that the PCMs are utilizing the latent energy to protect the product. Whereas in the case of water, water was just using its specific heat capacity in its liquid state. It was not changing phase. So we were not taking advantage of the latent heat of water in that case. And using the PCMs, these are the results against the new winter profile. And as you can see, once the temperature starts going below the phase temperature of PCM4, it starts changing phase and starts maintaining stable temperatures within the shipper. Here's another example. This is much more challenging, and this is basically CRT product shipments. So control room temperature shipments where it is required to ship against the ISTA 7E summer and winter profiles. The original design, these are proposed designs. The original designs were proposed for seasonal shipments, so one for winter and one for summer. So in the summer conditioning, you have essentially 2 layers of water refrigerants all around the product, as you can see. So the dark blue ones are conditioned at 5C, and the light blue ones are conditioned at 22C. So that's the summer configuration. For the winter, the configuration is changed, all the refrigerants, and then conditioned at 22C. The total refrigerant mass in this design is 22.5 pounds. So let's look at what happens using this configuration. So with the summer configuration against the ISTA 7E summer 48-hour profile, we can see that we almost get the required temperatures between 15 and 25. It starts hitting the upper limit right at the end. So it is a successful design. One thing to note here, though, again, that we are not taking advantage of the latent heat energy of the water. So all we are doing here is we are using the specific heat capacity of liquid water, which indeed is higher than most other materials, as Richard mentioned in the previous section. So that's one advantage of water, that it has a fairly high specific heat value. So let's go to the next one and see what happens in winter. So in the winter configuration, though, that really doesn't work. If you look at the results from the ISTA 7E winter 48-hour profile, basically, again, we are using the the specific heat capacity of liquid water, but it starts going down pretty quickly along with the ambient profile, and it just barely makes it less than 20 hours. So it doesn't do the 48 hours. And this is also a function of the ambient conditions as well, because if, as you notice in the winter profile, the temperatures are consistently below the min temperature of the product, which is 15C. So unless you have some kind of phase change behavior in the PCMs, you will not be able to maintain temperatures with this kind of profile. So what is the solution? Again, using a certain class of PCMs, keeping the same insulation container, but instead of using water, we use a selection of PCMs which have a phase behavior within the CRT range. So they change phase within the 15 to 25C range. All the PCMs are conditioned at 22C. So that's a big advantage. In the previous water-based design for the summer, we had 2 different conditioning temperatures. But in this case, all the PCMs are at 22C for both seasons. So we don't have to change the conditioning for summer or winter. So we actually have a universal design instead of a seasonal design. And also because now we are taking advantage of the latent heat energy of the PCMs, we are able to reduce the mass of the PCMs also. So previously it was 22.5 pounds of water. now we have 18.75 pounds of PCMs, so a reduction of 17%. That's also a big advantage. There's several advantages. You get rid of special conditioning requirements, you change the design from seasonal to universal, and you also reduce the weight. So we run the thermal model with these PCMs and look at this. You see for the ISTA 7E summer, 48 hours, flat lines. So it very likely will do more than 48 hours from the way it looks. So there may be some room to optimize some of the PCM mass there. And this is the more importantly, the winter one. Again, you see that in the previous water-based design, the temperature keeps going down because there's no latent heat capacity being used. Here, because the PCMs are changing phase within that range, you get a flat line for the full 48 hours. The final case study is another example of how to use PCMs to come up with a single design instead of two different designs, again, seasonal to universal. In this example, it's a simple two-sided design. There is a polyurethane container, which is using two frozen water refrigerants on the outside at -20, then two refrigerated water refrigerants on the inside, the light blue ones. We have to put a EPS buffer between the frozen and the refrigerated water because there could be a cold shock right in the beginning. To prevent the cold shock from the product temperatures to go below 2C, you have to put some EPS buffers in there, which are about 0.3 inches thick. So this design is meant for ISTA 7E ambient profiles for 36-hour shipments. And for the winter, we cannot use the -20 configuration because it will go too cold. So there's a separate conditioning for winter where all the refrigerants are conditioned at 5C. So this is the summer configuration against the 7E profile for 36 hours. So it works. As you can see, I had mentioned that there'll be a cold shock, and right in the beginning, you will see that the product temperatures do dip close to 2C, and that's basically because of the -20 bricks in there or -20 gels in there. If we remove the EPS buffer, very likely those temperatures will go below 2C. And this is the winter results where we have 5C refrigerants inside. Again, we get successful results between 2 to 8 for the ISTA 7E winter profile. In this case, there will be no phase change. Essentially, we are using the specific heat capacity of water to protect the product. So we want to go to a universal solution where we want to use a single set of conditioning as well as same configuration without changing anything during the season, during the year. We keep the -20 water gels the same, but the inner refrigerants, we replace them with PCM4, which is conditioned at 5C. So the conditioning requirements remain the same. The temperature conditioning requirements remain the same as before, but instead of using water, we're using PCM4. The EPS buffer pads are now replaced with simple corrugate pads. So that's an advantage that reduces the amount of space taken up by the pads and increases the amount of space inside the container. Maybe you can increase your product size. And more importantly, this becomes a universal solution. So you don't have to worry about summer or winter. It can be shipped year round. So those are the summer results for 36 hours. You can see successful 2 to 8 for 36 hours. And the same configuration, same conditioning for the winter. Again, full 36 hours, successful solution. So that concludes my section here.
Vitkar, we did have a question come in during your section around. You talk a lot about what's in the pack out, and you're referring to EPS a lot as far as the outer container. Why is that most commonly used, or what would you prefer, or what other options are there, or why is EPS the one that is in all of these? Is that to compare it to the rest of them, or from just speak to that a little bit if you could.
Sure. So EPS, if there's one reason, one driving reason for using EPS is low cost. So expanded polystyrene is one of the cheapest insulation materials around. So that's why it's used. For pharma industry, using packaging requirements involve cost optimization. That's a big factor in there. So using EPS, one of the reasons is that. Also, EPS is a much lighter material compared to other insulation materials like polyurethane or VIP. Does that answer the question?
I think so. Thank you very much. Thank you, Iftikhar. So now that we've kind of understood the overview of phase change materials and some of the applications as far as thermal modeling to get pack outs and on some of that aspects, I'd like to turn over to Dawn Mance to kind of cover considerations of PCMs in packaging in general.
Thanks, David, and good morning, everyone, or good afternoon or good evening, wherever you are around the world. So Rich provided a great background at the beginning of this into PCMs in general to kind of set the stage for everything. And Iftikhar just took those concepts one step further and explained the role thermal simulation plays in determining the optimal PCM solutions to use for the various packaging scenarios that we just went through. Over the next 10 minutes or so, I will expand on what we've just covered so far to further explore the practical factors to consider when creating a thermal packaging solution. So as I just mentioned, Iftikhar talked about the parameters that are critical in thermal packaging design to meet the performance needs for each unique project. Factors such as the placement configurations of the refrigerants in order to meet the various shipping duration needs, you know, if you need 24 hours, 48, 72, 96, or even longer. The temperature requirements, we talked about refrigerated, controlled room temperature, frozen, container weight considerations, payload capacity, ambient profiles, all of those things. Outside of those, there are additional considerations that are just as important with respect to thermal packaging design, regardless of whether you're shipping temperature-sensitive biologics, pharmaceuticals, vaccines, med devices, or really anything that's temperature-sensitive or perishable that needs to be transported. Consistent and proper pack-out is vital for ensuring safety, quality, and preventing costly destruction of compromised goods. One of the most important practical considerations for thermal packaging design is simplification in pack-out. You may have designed the perfect thermal protection system for your goods, but if it's not properly packed out, you could still damage the goods. Improper pack-out can often result in front-end issues such as cold shock that Iftikhar just talked about, or back-end issues such as the payload experiences a temperature excursion during transport. One of the most straightforward actions you can take to simplify pack-out is to use a single SKU as much as possible in your thermal packaging platform. Having a single or minimal SKUs is critical. This can be accomplished by using universal pack-outs, for example, that we talked about, versus seasonal pack-out, resulting in just a single pack-out. Also, whenever possible, being able to use the same size pouches, the same temperature PCM within a pack-out alleviates any issues with selection or mix-ups there on the bench when doing a pack-out. Along those same lines, being able to use common components and platforms across multiple temperature ranges is important. Design synergy across multiple components and platforms can help simplify pack-out by helping remove opportunities for error and ensuring compliance. This also has the added advantage of improving the speed of pack-out. So the goal here with everything is to reduce the number of touches. The less touches, the less opportunities for error. So simplification is really key in all of this. Conditioning of the PCM is another key consideration when creating a thermal packaging solution. Iftikhar, again, just touched on that briefly. How will the PCM be conditioned? At what temperature? Where? For how long? You know, does the conditioning area, the freezers and refrigerators have standard temperature profiles? Beyond all those considerations, conditioning time can dramatically impact the operational speed of pack-out and is a key area for temperature excursions to occur. In some pack-outs, the PCM must undergo secondary conditioning, or a buffer must be employed to avoid cold shock. Cold shock occurs during pack-out when the product temperature declines rapidly when it comes in contact with a PCM that's been conditioned at a temperature below freezing. An example of this is in vaccine transport. Many vaccines lose effectiveness on freezing. If a frozen PCM is placed in a shipper directly against the vaccine payload, the vaccine against that frozen PCM can be rendered ineffective. Secondary conditioning can result in long bench time to reach safe temperatures for pack-out. Also, this process adds labor, time, and cost. Most importantly, if it's not done correctly, it can lead to temperature excursions and damaged goods. Designing your system for zero bench time can help towards the overall simplification of the pack-out process. Temperature monitoring in your thermal packaging solution is another consideration and can play two important roles. First, like in considerations 2, 3, and 4 above, the addition of temperature monitoring can help with the overall simplification of pack-out. For example, during conditioning, which we just talked about, including a straightforward color change temperature indicator on a PCM pouch or fillable bottle can quickly alert the user that the pouch has reached a safe temperature for addition to thermal packaging. A second role of temperature monitoring for inclusion in your thermal packaging solution is for temperature stability during transport. Many options exist from low-cost, simple go, no-go temperature indicators all the way to Bluetooth-enabled high-precision temperature and RH loggers to provide detailed time and temperature data that can be read throughout the shipping channel and accessed from the cloud from anywhere around the world. One example that encompasses everything we just talked about is a product called Protego that we developed for use for pharma and medical device sales reps to use during their daily routine of visits to hospitals and doctors' offices. The thermal packaging needed to be easy to use and keep the payload between 15 and 30 C for the duration of a typical 8 to 10 hour workday with multiple opens during the day. With a focus on simplification, the packaging was designed for minimal touches and ease of use to minimize any potential for error and the possibility of an unintended temperature excursion during use. Using our Adaptec Shift PCM gel pouches, the pack-out is so simplified the reps actually don't even have to remove or add anything to the thermal carrier. The PCM pouches are removable but are designed to remain in the carrier at all times. Conditioning has been simplified to the extent that the user only has to open the carrier and expose the inside of the carrier to room temperatures overnight to recondition the PCM. Again, essentially eliminating any user error. In addition, for this type of user experience, ergonomics was a key consideration. Not only does the design provide for necessary thermal protection, but it does so in a lightweight, attractive messenger bag configuration. David? Another example that highlights the considerations we just talked about is in the case of live animal transport. In this case, PCM pouches are used to provide safe and comfortable transport conditions for shipment of live animals year-round. Again, simplification and design was a driving factor in the final configuration of the shipper platform. Simplification of pack-out, straightforward conditioning, and use of common components allowed for a streamlined, error-proof pack-out process to ensure the thermal packaging works each and every time. By simply adding the correct temperature PCM pouch to the shipper, the user was able to expand their shipping channels and times of the year that they could ship. And in this case, the thermal packaging solution is truly saving lives directly. There's a few other considerations I'd like to discuss quickly for thermal packaging. The first is the form factor. As Rich mentioned earlier, PCMs are available in many forms. For thermal shipping applications, the most common forms are single-cell pouches, flexible pouch designs, bricks, panels, and fillable containers and bottles. More novel options include incorporating the microencapsulated PCMs that Rich discussed, and incorporating those into foams, EPS, plastics, and coatings. And David will touch on those more in a few minutes. A second factor to consider is product end of life. Product end of life has become a driving force in raw material and component selection as more companies move to provide sustainable products. For example, does a single-use disposable pouch fit your market application best? If so, is recycling or compostable materials important to you and or your customers as sustainability grows in importance? If you're transporting high value items and or shipping over the same channels repeatedly, does reverse logistics make sense by implementing a return and reuse option to eliminate waste streams? Those are all different options that have to be considered, which kind of leads into cost versus value. Cost and value should be considered hand in hand with both the form factor and the product end of life selections. There's trade-offs between cost and value, and those aren't always apparent or easy to calculate. An example is a higher initial cost option that may result in more value in the long run, such as a higher cost reusable option that can be used multiple times. Another example would be the trade-off in cost of a recyclable, compostable, one-time use product versus one that will go into a landfill. You know, what is sustainability, environmental stewardship worth to your company and or to your end users, which leads into the value to your customer. In the end, the best design for thermal packaging will offer your customer peace of mind that the product has been delivered safely in an easy-to-use, low environmental impact solution. For you and your company, a well-thought-out thermal solution results in a robust and simplified packaging system and process that reduces the potential for operational errors, provides your customer with an exceptional experience, and protects your brand integrity.
Thank you very much, Dawn. I appreciate you going over all those considerations as you go through each individual use and case study moving forward. So as we've talked today, Rich handled an overview generally of the technology and the idea behind phase change, the phase change technology. Issachar brought us up to speed about the designing and the thermal modeling that can be done to alleviate testing time and cost moving through the process. And Dawn covered the considerations of actual products that we, actual solutions that were going on and what went into that process. So I would like to cover kind of the technology that we had inside of that, what we brought to the table as Kavu and how we were able to help our customers and help our specific cases for that process. So to specifically start with the live animal transport that Dawn talked about, as she mentioned, this was literally a life or death situation. And as Rich commented earlier, most of the time, a lot of the temperature thermal packaging solutions that we talk about are around frozen, refrigerated, or CRT. But this was a comfort area kind of outside of our normal comfort zone, something that goes above the CRT area. And it needed to do that to make sure that the shipments could last as long as they did. The benefit that Kavu brought to the table was in our AdaptTech line of products that we can go from -20 all the way up to 43°C. We can meet whatever temperature profile our customer or partner needs. And we can not only just produce them in a large single cell heavy pouch, but we can also create them in a multiple cell sheets. This allows for protection to cover a larger area, covers it more efficiently, as well as gives intimate contact to the product or payload. This intimate contact can take it 4 minutes wrapping around something or sliding in a specific sheet. So you see here the fact that the AdaptTech product has multiple cells, multiple aspects in a sheet, and that allowed us in the live animal transport to put it underneath and in and around the payload at this point. That was allowed to not create hot or cold spots. It was able to lay neatly on the bottom and cover it from that standpoint. Because these sheets are typically flatter and they have multiple cells, oftentimes you can achieve a benefit from a thermal management standpoint that's much more efficient and adds less weight than a single cell in certain cases. The Protego carrier that we talked about added the benefit of multiple cells with our AdaptTech shift technology. This shift technology was able to fit into a narrow pocket, but also allow the change of material to not creep because it is a shape-stable gel. This technology holds the form of the PCM when it's in its solid or liquid state. In the use of the Protego carrier, it was being carried in and out of the car, in and out of air-conditioned offices. And as Dawn mentioned, the pouches were inside of the wall, and the sales representative did not need to remove them to make sure that they worked each day. So the benefit could not be seen, and the sales person would not be able to know whether or not the material had fallen or creaked. So this was able to give the benefit of the PCM in the right spot of the carrier all throughout the day. It gave the same protection at the beginning of the day as it would at the end of the day, because the gelled material would stay in the same spot. It also prevents it from leaking. So if there is some sort of catastrophic puncture or failure, which is unlikely of the seal failing, but it's important to know that the material would stay in that spot and would not be moved or fail in any aspect from that standpoint. This product would be taken in and out, and it would hold up for a long period of day of 8 to 10 hours. Finally, I'd like to talk about our Adaptec Endure product. This is an exciting product of ours. As we talked with Rich earlier about the microencapsulated aspect and the macroencapsulated aspect of our technologies, this takes the microencapsulated phase change material and encapsulates it into a polymer rigid form. This image shows our technology specifically as a panel or a sheet, but this form can be used very similarly in any packaging scenario that we just talked about. From a pouch standpoint, we can now put it in a panel. This form, there's zero way for it to leak out of the product. The integrity of the PCM will not be compromised unless there's a deliberate cutting or bending of this product. This rigid material also provides a shock or puncture protection, not only to the PCM, but also to the product inside that it is protecting. In this form that we see it right now as a sheet, is just one of the many ways that this product can be used. If you can imagine any sort of aspect of a plastic or a polymer, we can add our Adaptec Endure technology to that product. So any dream that you can have of something in a plastic form can now have a plastic form that is also thermal management and thermal protected. The group, we've specialized in thermal management and thermal management protection, and these are just 3 of our technologies. So we have the aspect of having it in a panel form. We have the aspect of gelling it into a more of a sachet, multiple cell aspect, and we cover contacts from -20 all the way up to 43 degrees. So we work directly with our customers to make sure that we have the most beneficial solution for their specific need at that time. At this time, we'll have some questions. I know that there was at least a couple of them that came in. One of them specifically came in. Rich, I'd like you to speak to this if you could. You mentioned a lot of different types of PCMs. Can you speak specifically about the difficulty of using organics versus salt hydrates in manufacturing, as well as leaking and other options go?
Sure, David, I can answer that. So,
Rich, before can you fix your microphone one more time for me?
How's that?
That's much better.
Okay, so as far as the manufacturing is concerned, it's important to note that for these salt hydrates and the salt water solutions, the reason that those are generally considered, again, in my experience, to be very difficult to package without leaking is that a couple of things. One, those materials generally have to be thickened because either the salt or the salt hydrate, because of density differences with the water that they're in, can basically settle out on the bottom of the container or the pouch. And so that's a big consideration in terms of making sure that the mixture is homogeneous. Because if the phase change material isn't if the phase change material itself is in one location and the water that it's supposed to be mixed in with is somewhere else, then you're not going to get the full benefit. The other thing is, again, what I've seen from my experience is that with packaging machinery, because salt hydrates and salt water solutions tend to have actual solids that can plate out, sometimes that can get fouled up into the jaws of the sealing mechanisms of the machinery, and that makes it extremely difficult to make a seal. It's very difficult to make a thermoplastic seal through a rigid inorganic material. And that's basically the summary of why I included the characterization of organics versus inorganics the way I did. Hopefully that answers the question.
Thank you very much, Rich. Iftikhar, a question came in. There was a lot of reference that you made as far as profiles go to the ISTA 7D and 7E profile. Can you kind of expand on that a little bit, or do you know the differences between them, or how, why you would use one or another?
So ISTA has developed these profiles based on their study of various shipping lanes over the last 15, 20 years. And the ISTA 7D standard was developed first, and that was specified for different durations of shipments, like 24 hours, 48 hours, and 72 hours. And it was not based essentially on data collection. It was more based on how people kind of understood the shipping lanes. So at some point, and I'm not sure exactly the date, but it was I would say at least more than 6-7 years back, that ISTA developed a more data-based profile, which is known as the ISTA 7E standard. And that's where they actually used shipments throughout the continental United States over a course of a year or so, and collected data, ambient data, and used that to develop these profiles. There is, the industry uses it for qualification of packaging. The ISTA 7D is a more extreme profile. If you look at those profiles, it has, like the summer profile has soaks of 35C and 30C, and the winter profile has cold spikes of -10C. But whereas the ISTA 7E profile is more representative, the summer profile is much more representative of the diurnal cycle through the shipping lane. But the winter profile is not as representative. As you could have seen some of my examples. It shows that the winter temperatures just keep going somewhere, above zero. And that's not a very realistic representation of some of the shipping lanes. The temperatures can go below zero. So those are some of the, pros and cons of these things. Generally, ISTA 7D would be a more extreme profile compared to ISTA 7E.
Thank you very much. That seems to be the last question that we had come in at this point. However, if you do have any other questions, here is the contact information and titles of the presenters. I want to specifically thank each one of them for their time today and putting together these presentations for everyone. And I would like to thank everyone for attending this PCM Masterclass. Hope that it was informative as well as educational. Again, if there are any other questions for us, feel free to email them directly to any of us. If we don't have the answer, we'll find it from the other person on the panel with us. So thank you very much for your time today, everyone, and enjoy your afternoon.